Good afternoon, everyone. My name is Galațanu Sergiu-Valentin, and today, because the PhD student Ionut AILINEI can't be in this beautiful Iceland and in the great conference, I will do the presentation of the paper, The Influence of Anisotropy on Vibration Behavior of S600Mc sheet metals. The presentation structure, I will start with a short introduction about sheet metals, some general aspect about vibration, some information about the specimen. I will discuss about the experimental procedure, the main results, what we calculate after, and in the end, the correlation between experimental investigation with finite element analysis. In the end, some conclusion and some future works. As all know, that sheet metals anisotropy is the directional dependence of mechanical properties. It is a critical factor that must be considered when using numerical simulation to predict any manufacturing process involving plastic deformation. On these slides, I present some application from automotive. The application that is important for us are the brackets from the seat belts. The objective of the paper is to determine experimentally frequency response function, natural frequencies, to calculate the structural damping, take into account Q factors for each direction in order to explore the vibration behavior of the S600Mc specimen. In the end, the determined parameters were used for computation calculation of the natural frequency using finite element analysis. As you know, here is the equation of the motion, undamping, where m is the mass, k is the stiffness, matrix U is the displacement, and if we introduce the displacement and the second derivation of displacement in the general equation, we receive the eigenvalue equation. The failures due to vibration loads are caused by the peak G, loads expressed by the device under test. Most products have a resonance frequency in the testing range. Resonance frequency, transmissibility, and Q factor are a determined factor in vibration induced failure. A product is subjected to fatigue loading when it is exposed to its natural frequencies. The transmissibility is the ratio between the input of the acceleration input of the controller channel and the response channel. Also, bandwidth of resonance is computed as the distance in hertz between 3 decibel drops-offs on each side of resonance. This is also known as the half power band method. The Q factor of resonance is defined as the ratio between the central frequency of the resonance and the half power bandwidth of the resonance. The Q factor tells us how sharp or steep the resonance is. With the Q factor, we calculate also the damping for our material. We use the test specimen according to ISO 10130 with a thickness about with 3 millimeters and the width 12.5 millimeter and the length gauge about 75 millimeters. The specimens were laser cutted on different direction, taking into account the rolling direction. We have a specimen at 0 degree, 45 and 90, 3 specimens from each type each angle. We use an electrodynamic shaker to generate the force harmonic motion to exercise the specimens. Piezoelectric accelerometer were used to measure the acceleration response, and broad bands in sweep vibration profile was used, ranging from 10 to 1000 Hertz, with a constant acceleration of 1 g, having a linear sweep rate of 1 Hertz per second over the entire spectrum. One run we did for every specimen. On this figure, you can see how the specimen 2 are clamped fixed on the electrodynamic shaker. In the back part is the input acceleration, and here are the piezoelectric accelerometer who measure the response of the specimen. Some results on this slides are present the results for all three specimens from every direction, but they are very similar, and seems to be only one, but are three here. Well, better we will see on the next slides. And the normal mode 1, 2, but this is the third normal mode, because this from here is not a noise, it's the second natural mode. We will see it on the finite element analysis better. What I didn't say is that the accelerometer, our piezoelectric accelerometer measured the acceleration only on that direction. Some results, if we look to the first resonance frequency means and the second, for the first we have very similar results. Some difference is for the second resonance frequency mean. But if we look to the amplitude, for the first amplitude we have some difference. The biggest value were obtained for the 45-degree specimen, about 164 G. The lowest value were obtained for 0 direction, and if we look to the second amplitude mean, the lowest is for 45, and the specimen at 0 degree. Taking into account the results, and we calculate the Q factor, and with the Q factor next we calculate the damping correspondent to first frequency mean and to the second frequency mean. Some difference were obtained depending on the direction of the specimen. And in the below part are presented the damping corresponding to the first and second frequency, damping ratio for all the specimen, all 9 specimen. For finite element analysis, we use in this case ANSYS. We import a simple geometry for our specimen. We create the boundary condition of fixed support, and we introduce the acceleration about 9.806 meter per square seconds. We use hex elements for the mesh, and here we can observe the normal mode, the mode 1, who is out of plane, bending this one, the mode 2, who is in plane, and this is what I said, that on this graph it's what this noise that we have it here. And mode 3, it's also out of plane, and it's second order bending. Unfortunately, I don't have all the results from the simulation because the hard disk was burned, and this is the only photo that I had it on my phone. And now we need to redo all the simulation. And but here you can observe a very good correlation between test and simulation results. And also we did a random vibration profile, and we did good correlation between the experimental and finite element method. In the end, the vibration measurement showed that the anisotropy generated by the rolling direction has a big influence on the damping ratio. A good correlation was observed between a finite element model and experimental investigation. Next, we want to do some product test on our brackets, to do some fatigue test to fail these brackets. Also, we did some impact test to see the anisotropy on this, and last year we had also some tensile. Thank you very much for your attention. Next year, Timișoara will be European Capital of Culture. Hope you will visit Timișoara. We will have 100 years from our laboratory next year, and also a very nice conference in March. Thank you very much.
Well, thank you. Thank you very much for your nice talk. We have time for a quick question from the audience or comment. Okay, well, maybe I can ask you some details about the convergence that you performed in your model.
Yes, we had a lot of problem with this. Also, yesterday we start to redo the model, and we introduce two damping factor. For the first mode, we introduce what we calculate here. Yes, this. And normally what we have on this is the problem, because this is also a normal mode. And if you told to us is that you have the damping there, you need to know what damping. And we try to calibrate a little bit to ignore this normal mode and to put only the damping factor for the third normal mode.
Okay, well, thank you very much.
Welcome.
Thank you again. Okay, we